Okay, so alpha decay is a lot easier to get our head around compared to, it's a lot less strange than beta decay is. So I'll just put that up there. We've got here polonium, and polonium is going to decay. It's going to undergo alpha decay. So again, the word decay describes the process, the stuff that is given off that we detect with our Geiger counters or Geiger Muller tubes. Then that's the radiation. In this case, it's going to be an alpha particle, alpha radiation. So let's see what's going to happen. We've got polonium, and it's unstable, so it's wobbling all over the place, and then it becomes lead. Let's reset that and do that again. So polonium, which has got a mass number of 211, becomes lead. And eventually did it a lot more quickly. But the fact that it does it over different, you don't know when it's going to happen. That's what it's trying to demonstrate, that it's unpredictable and spontaneous. So mass number of 207. And it also gave us something called an alpha particle. And nothing else, actually, in this case. So if we look at a periodic table, we should be able to come up with find the atomic number for polonium and the atomic number for lead. So do you want to just do that?
Yeah.
Right, so looking at that example, we've got polonium, the mass number went down by 4, and the atomic number went down by 2. So, as I said, this is a lot easier to understand compared with our first example. If we look at our first example, we had of beta decay, we had carbon-14, mass number of atomic number of 6, became nitrogen-14 with an atomic number of 7. This is confusing because the atomic number, the atomic number increased. We didn't give it anything, but it increased, and the mass number didn't. It stayed the same. So that was confusing. Eventually, we realized one of the neutrons became a proton when it did that, and it gave off a beta particle, and that was the radiation in that case. In this case, it's a lot easier to understand. The mass number's gone down by 4, the atomic number's going down by 2. So I'm going to pause the video. I want you to think about what has actually happened to cause the atomic number to go down by 2 and the mass number to go down by 4. So it's lost 2 protons and 2 neutrons, which would produce a mass number of 4 and an atomic number of 2. So therefore, the alpha particle must have a mass number of 4 and an atomic number of 2. Now, in the case of beta decay, beta radiation, we identified that as an electron. You kind of had to take my word for it there. I was like, it's an electron. But in this case, you can actually work out what it is, because we know it's got an atomic number of 2 and a mass number of 4. We actually don't need to know what the mass number is, we just need to know the atomic number. So when you look at the periodic table, you should see what it is. What is it? Yeah. So exactly. So this, in the first case, it'll say what is a beta particle? It's an electron which came from the nucleus. And in this case, we would say it's a helium. And we must say it's a helium nucleus because it doesn't have any electrons. We only produced, all this happened inside the nucleus. This is why we call it nuclear physics. Right? Nuclear just simply describes of the nucleus. It's just an adjective to describe the nucleus of an atom. So nuclear physics is all to do with things going on inside the nucleus of an atom. So we've taken the nucleus of polonium, an unstable one, and we've watched it, and it's just decayed into lead. And when it decayed, it gave off this thing here, and under closer inspection, we see it's got a mass number of 4, atomic number of 2, and therefore it must be a helium nucleus. Okay, a lot easier to understand than beta. Well, it's a lot less strange than beta decay. Why it happens in both cases is weird. And this thing down here, you don't need to know. I don't think you may need to know at A level. But essentially, it just means that this blue line, yeah, it's a graph. It's an energy graph, and basically, it's saying that these particles don't really have the energy to get out of this kind of well. You can think about it as a well, and but they do something called quantum tunneling, where they just basically get out anyway. So I don't have enough energy to do this, but I'm just going to do it anyway. And that's what quantum physics is all about. That's why quantum physics doesn't make sense. So it's like in quantum physics, things just happen even though they're not supposed to happen, and so it's like things average out and everything follows the laws of physics. But every now and again, you'll get something that will break the laws of physics, and then which obviously just means we don't understand the laws. We've not written the laws correctly, because we don't dictate the laws. We're trying to describe them, and we obviously didn't do a very good job of it. But you don't need to know this for GCSE. You just need to know what I've talked about down here. Okay.